Welcome. My name is Torbjörn Nordling, and I'm an assistant professor in automatic control at the Department of Mechanical Engineering at the National Shandong University in Tainan. Behind me, I have the first building of Tainan Technical College, built in 1930 to house the original three departments: Department of Mechanical Engineering, Department of Electrical Engineering, and Department of Chemistry. It's now my pleasure to introduce our honorary chair, Executive Vice President, Chair Professor Wu.
It is a pleasure to welcome all of you on behalf of the National Shandong University in Taiwan. I'm proud that our team, the NCKU Parkinson's disease quantifiers, are one of the finalists in the OnCV&AI competition. They are also arranging this workshop. Now let us all learn computer vision and AI using the OAK camera together.
It's my honor to introduce Brandon Gilles, the CEO of Luxonis. Brandon obtained his master's degree in electrical engineering from the University of Colorado Boulder in 2009. Brandon is on a mission to improve engineering efficiency by embedding spatial AI and computer vision into products. He is the creator of the OAK camera that we are using in this workshop.
All right. Hi, everyone. Thanks for taking the time to watch this presentation. So what I'm going to go over today is Commute Guardian, which is still a concept, but remains as DepthAI's North Star and is the whole reason we made the DepthAI OpenCV AI Kit OAK series. So this is all about embedded, performant, spatial AI, and CV, which I'll detail more in just a little bit here. So to go with good to great, the book, start with the who. So Double E, always been driven to do something that matters. I'm currently viewing the way to do something that matters as making it easy for folks to embed embed performant spatial AI and CV into products. So taking all these mature things that exist and are incredibly useful on big things and making it so you can make a little thing with them, but make it easy so it's not like designing a complicated web app in the 1990s, but rather a complicated web app experience in say 2021, which is actually quite nice and low technical risk. And so I'm on a team that's obsessed with those five things. As I think it was from 0 to 1, he talks about any company that does something that matters is a bit like a cult. And the only difference is the cult is wrong about the secret they believe in, whereas the company of these diehards on what they believe in are right. And we think we're right on this. We think it's going to have a ton of value. So we're obsessed with these five things: embedded, or allowing you to embed performant, spatial, AI, and CV into actual products. And we think that's going to have a huge impact. So currently, it's really, really hard to do. And simultaneously, we think it's going to be insanely valuable. So, why are we doing this? Pressing health and safety problem. This is an accident, as you can see, and I'll highlight later, in a school zone, where fortunately this truck hit a car, and it was just from distracted driving. Not a bad person, just distracted driving. Escalated quickly. So you can see it, hit the car, and then just glanced off of it. Fortunately, there was no one on the sidewalk, but it hit hard enough to, you can see, rip the wheel off and do a ton of damage. Fortunately, everyone was fine. But as I wanted to accentuate, this car rolled over in a school zone, or this truck rolled over in a school zone. This is kind of like typical American car, if you will. And this is just distracted driving. My business partners hit a sign. I've been in distracted driving situations. I actually had one where a cyclist saw me swerve because I wasn't paying attention and could have been putting a cyclist at risk. And the real question here is, what if they hit a person? No one was hurt here, but you can see the amount of damage that was done even to this vehicle. Unfortunately, for me, I was in a car, so it's just a fender bender. My car got kind of messed up. I was lucky; it's just a beat up car. But 4 others in my circle were not so lucky. So one died; he was just hit by a mirror. One got a traumatic brain injury, and then the 2 that got off the lightest both had broken backs, shattered hip, and shattered femur. And the luckiest of the 2 was bedridden for 9 months, and his life will never be the same. But at least he's alive. So why are we doing this? A fender bender impact, if it's against another vehicle, is just that, it's fender bender. It's no big deal. If it's against a person who is not in a vehicle, that can kill him. The guy who died in my area, founder of a popular hackerspace near me, was just struck by a mirror in the back of the neck. And so it probably didn't even damage the truck that hit him. So if you're walking, if you're riding a bicycle, we're specifically focused on folks who are riding bicycles, but this could be used on other forms of unprotected transport. This is a huge deal. It's not just hurting personal property; it's ending lives. So I was hit in a vehicle by a distracted driver, fortunately, and there was no one on that sidewalk. I've also had the situation where a car just narrowly missed me while I was riding a bike because they were texting and driving, and that's the only thing that like woke them up is they hit the curb, went over the curb, and then went back down. And so I had been interested in could you solve this sort of problem for a while, and so had this gentleman, Jonathan Lanzi, who started Loud Bicycle. And he puts the marketing really well when he says speak car. So this is what's considered a highly sensory compatible input. He did this Kickstarter in 2012. You can still buy it today. It's extremely useful. Actually, a lot of folks use this already. But one disadvantage is it turns out just the physics and the permutations of accidents, you only see less than maybe 20% of the cases. Like you as a person riding a bicycle can only tell in fewer than 20% of the cases that you're going to be run over. So all this is extremely powerful and effective. When you do see you're going to get run over, often you don't. Less than 1 in 5 of those times do you see that you're going to get run over. And so I already knew about this. I feel a bit bad. I did not back it on Kickstarter back in 2012. I really liked it though. And so after this happened to the kind of friends of friends in my circle, I immediately thought back to this and reached out to Jonathan Lanzi, and he was extremely helpful. And I was just curious, well, with all this AI and CV that's breaking records in all sorts of situations, could you make a bike light that could just see the remaining 80% of the time when you can't? To kind of imagine like this product, but just with like your buddy on the back of your bike, looking out for you. So that was the premise and the idea behind the Commute Guardian concept, the Commute Guardian idea. So this actually, my wife made these years ago when we were first thinking about this. This is just to visualize it. You wouldn't necessarily need to have something on a smartphone, but you could with something like this, where really this is just wanting to show the 3 different conditions. So like all clear, like you're fine, it's just normal biking. And when you're commuting on a bicycle to and from work, you have probably 500 to 1,000 people, at least in urban, suburban areas, that safely pass you on a road. You don't really care about any of those. You just care about the one that's texting and driving or otherwise distracted that's on your trajectory. And fortunately, to save your life and also to save the experience of that driver, so they don't have to have that on their conscience, it's relatively little action needs to be taken to prevent the accident. A couple inches of swerve is enough, and Loud Bicycle proved that a car horn will get that for you pretty safely. It's highly sensory compatible, meaning that it talks to the inner lizard in your brain. So it happens fast. Whereas other things that are not sensory compatible, like trying to yell at the car, it has to engage your conscious brain. So that results in taking too much time and you only really figuring out what happened after you've run the person over. So here's an example, all clear on the left. the idea, there's actually probably more feedback mechanisms than this, but you can do haptics onto the bike. Fighter pilots use that to know where missiles are coming from because they're a highly sensory compatible input. Because we're very used to like touch, and touch being associated with danger in situations. So all clear. Haptics are off. There's LEDs. The idea here is that it's a bike light. So LEDs that say would be too bright to just be flashing all the time. You can strobe those really bright when there's actual danger sensed by this kind of like artificial buddy riding on the back of your bike, figuring out if you're in danger, if a vehicle's on your trajectory. And then the idea is straight from a loud bicycle, a car horn, an activated car horn. So imagine a loud bicycle. The car horns are actually relatively small. They're like this big. That's only for the oh shit moment at the very end. So in the warning stage, someone's on your trajectory, but maybe they're rounding a corner, but it definitely doesn't look that great. It gives you haptic feedback. It starts to strobe the LEDs just to give you a bigger visual presence. But if someone's really, texting and driving hard, like their eyes, the cone of vision doesn't even like leave their dashboard or even their phone, maybe strobes won't work. And so that at the last minute where there's still enough response time, just barely a buffer on the minimum response time for that swerve, then you do the horn. And the large question here was, there's kind of two sides. Is this really possible? If you talk to autonomous driving folks, they're like, well, of course. If you talk to a normal person, there's no possible way. I was actually kind of in the middle when this whole life context occurred. So I wasn't really sure. So I ended up prototyping it at the beginning, which there's a whole bunch of ways actually you could solve this. Whether you're trying to figure out like the 3D pose of the vehicle, for example, or using neural inference to figure out pose and position and trajectory, or you're doing depth sensing separately. And what it came to after like a whole bunch of investigation and trades is that spatial sensing, some form, is necessary for it to work well. Disparity depth is great for this sort of problem because of the speeds involved, the relative trajectories and depths. So you can get 30 meters out of OAK, which I'll cover later, that we actually put on a bike. I'll show that later too. AI to know what it is, that it's not just a gaggle of bikers, for example, because if you use spatial sensing only without AI, you get all sorts of false positives, which is what autonomous driving folks were like, of course, this is solvable. Normal people were like, the main concern, folks who don't work in that industry were super concerned about a gaggle of bikers setting it off, or another biker close passing you and setting it off. With AI, the risk is effectively zero there, or could be made as accurate as a person activating the horn, probably. And then a whole bunch of CV stuff similar to, when you're running around or walking, your head's bobbling all over the place. When you're biking, the bike is kind of waving back and forth as you pedal and so forth. But it was pretty reasonable to tie these together to solve this problem, which is effectively quantizing risk and taking some action based on the real-time quantized risk to warn the person riding the bike, and to also warn or wake up from distracted driving the person driving the car. So the 5 things, and this will be like the theme of this presentation. So it's like maybe like micro memorize these, or it's embedded, performant, spatial, AI, and CV. So performant meaning you really do need like high resolution, high frame rate, multi-image sensor, like 4K video encoding, the capability to handle 12 megapixels. So in the cars, moving quickly at a distance, so forth, you can still like OCR license plate, for example. Spatial, obviously, to know where it is in physical space. AI to make sense. CV to tie it all together. And embedded, I can't use the iMac that I'm recording this on very tentatively on on a bike. It wouldn't last very long. So like a true embedded system where it's small, battery powered, relatively lightweight, can be made in the form factor that you want, and importantly has the embedded system power modes so that it can actually last quite a while, maybe 10 hours. So we ended up in a pretty interesting situation when trying to see if this could be solved, where when I went and asked people who are actually good at this stuff what they thought, they were like, of course you can solve this. And I talked to a lot of folks, went to a conference where the CTO of Waymo was there, and even got to ask him by like, as he was getting off the stage, like being that person. And he probably had what turned out to be the most accurate answer, which is like, of course you can. Like this doesn't work really well. I think it's a good idea. And then like as starting to walk away, but I don't work in that industry. We have a lot of literal power, compute power, everything. Size, weight, and power could be an issue. I'm not too sure, and it certainly was. The first prototype was huge and consumed a bunch of power and wasn't sufficiently performant. The compute was actually there. There was well enough compute power, but it wasn't tied together in a low latency way that allowed you to have the frame rates necessary. But the Myriad X existed, which was, for all intents and purposes, I think architected to do exactly this. I don't know the full story on it, but it really does seem like someone spent their whole career architecting to solve this problem in advance. It has 120 frames per second, a million depth points, stereo depth, dual core AI that can do 60 frame plus per second object detection. That's unoptimized neural networks, so it can probably go a lot faster than that if you're willing to dig into the neural networks and run, probably 4 or 5 of them in series, all doing that. 36 core CV accelerator that had these varying degrees of flexibility. And then importantly, like the proof of concept that I threw together had actually more than all of this, but would only run at 3 frames a second because of the data path. The data path is extremely important on stuff like this, where the image sensor coming in is quite literally, let's say, 1 gigabyte per second, which is a lot, right? Like that hardly fits over USB 3.1, 10 gigabit per second. It probably wouldn't realistically, even to my like the highest end iMac that I'm recording this on. And so data path is super, super important. And in this Myriad X, it has a network on chip, so it can handle 1 gigabyte per second of image sensor data coming in, and then tie it together with this prioritizable network on chip. And then it has a dual core CPU, which then allows you to run all your business logic between multiple stages of AI, CV, and other pieces. So we saw a need for this. This being new technology, I'm a huge believer in just trying to get this out to the world, because I don't think I'm smart enough or have enough life experiences to know how such a thing can be used. And we were blocked not by a lack of existence of the chip. It's super exciting that the chip existed, but there was no development platform yet, at least, that allowed you to use the chip in the way that it was architected for. And I think it's just because everything was so bleeding edge. So we had a choice to just kind of like give up, or say, well, it's quite lucky that the chip already exists. Why don't we make a development platform around it? And we already tended to be good at that sort of thing. Not exactly that, but close. So we did that, and that's a lot of what this talk is about. We did this Kickstarter around it that we've since fully delivered on, to try to get this out to the world, to folks that are aware of problems in their industry that we're not aware of, that we can accelerate their capability to build their thing of value. So whether that's just some guy in his basement with an idea, or that's some company that's been stuck. Maybe they don't even have CV experts, right? Like they just know their industry, and an enterprising engineer sees it and says, okay, well, I could totally change how we do things in a really valuable way, if there's a low risk way to do that. So that's the whole purpose of this platform. So what is spatial AI and CV? That's what this kind of comes down to. AI with computer vision, AI and CV is all about what are things and where they are in pixel space. Spatial just means physical space, right? So I just picked up this PCB, like I can point to each thing because I have 2 eyes, and the spatial information helps. And on the 2 eyes actually really helps. I play volleyball with a person who lost vision in one eye, and before they lost vision in one eye were world level competitive. So even for what, and as far as I know, the most intelligent beings that exist, humans, not having stereo information is hugely detrimental for interacting with the world, especially if you need to do it real time. So that's what spatial AI and CV is. It's integrating spatial information with AI and CV to be able to have this real-time interaction with the world. So here's me jumping around my office to give an example. Theoretically, I I guess even the play buttons don't work on demos, so I'm just going to scroll through here since it won't play for me. So what this is showing is a colorized jet OpenCV colorization of the depth information, then with MobileNet SSD object detectors that sees chair in person. And it's a little hard to see, but it's overlaying my full XYZ position. This is doing average of that internal bounding box, but there's all sorts of other algorithms you could do, like edge of me and so forth. So this is a very basic example of spatial AI. Another one we have is running semantic segmentation. So it semantically labels all the spatial pixels, which could be really useful in the Commute Guardian example, which we've only run inside on a person so far. So we'll do that soon. Here's another overlaid actually on neural. It won't play, so just fast forward here. This is actually kind of better. So without, you can do this on like, big robots when you combine like a depth camera and a computer and like an AI processor, but then you have to figure out all your sync mechanisms. Since the Myriad X is actually architected for all of this, it syncs that all together via the network on chip. And so you just get pre-synchronized results that just pop out, which just makes everything easier. And then you just don't have to spend all that time. Okay, so what this really means, the Myriad X is kind of the beginning of a new era in embedded systems. So traditionally embedded systems, it depends on who you talk to, but generally you're not going to try to use an embedded system to do some like crazy high performance CV task, particularly one that doesn't even run Linux. And so the Myriad X is kind of this interesting beast. The thesis was, well, with AI now making sense of a lot of things, and if you just accelerate specific tasks, all you really need is an embedded systems like coordinator. You don't need all of the extra that comes with running Linux. So this is kind of the first chip that allows this. There's a lot of embedded things that can do AI at low frame rate and so forth. There's a lot of Linux systems that if you throw a lot of power at them, will maybe be able to do this level, but this kind of takes the best of both worlds to make it smaller, lighter weight, more deterministic, and no full Linux you have to run, so you can boot in seconds, sort of thing. So digging deeper into the Myriad X, the idea, the premise here was this like asymmetric multiprocessor meets embedded systems. So asymmetric multiprocessors were very popular in the late 90s. My understanding of the histories here is actually relatively limited, but for like being an electrical engineer, being curious about this stuff, what I remember and saw was those came out. There are these theoretical gains of, it's going to be 1,000 or 20,000 times faster because we have these like 30 different cores that do these different things. And then that like met the hard impact of reality, which is kind of a core of science, right? Beautiful hypothesis meets the hard reality, which was, okay, now you had 30 or 40 cores. And so for a programmer, at least in the late 1990s, that meant that you had to learn not just one architecture, but 30 or 40, which just meant that people didn't do it. And so where you had theoretical gains of 1,000 to 2,000x or something like that, that all just vanished because it was too hard on the programmer to learn all that. And so really it just meant that most of the system was just not used. So the thesis with the Myriad X was that, well, why don't we use modern tools? Modern software tools are way better than this first experiment in the 90s. And you could build an abstraction layer where you get to take advantage of all this asymmetric multiprocessing that allows these huge gains in performance per watt and so forth without a load on the programmer. And so that's a 16 vector processors, GPUs, but architected specifically for computer vision, 20 fixed function CV processors. Turns out there's a ton of common CV functions you're going to have to do if you make dedicated hardware and a chip with a network on chip to tie it together. You can do those at 1/100th or 1/1000th the power, if not just significantly higher frame rate at the same time, to AI processors, and then dedicated depth hardware, which is again perfect for what we were trying to solve. So this chip existed, but there wasn't a way to even use it on hardware. So we were searching desperately. Fortunately, if you need to do AI, so I talked about the 5 things, embedded into something, have it be performant, high resolution, multiple image sensors, high frame rate, spatial sensing, AI, and CV. If you wanted to do AI, you could do that. You could buy a little accelerator card that would let you run AI, or a neural compute stick 2 that would let you run AI, but those other 4 things just vanished. So one of the first things we needed to do was actually design the hardware that would allow you to run the chip this way. The software ecosystem and firmware ecosystem didn't exist, so we had to do that too. But importantly, there's hardware. So you can permute, you can build things, and they're all open source. You can buy it. All the design files are available, the full Altium files. We wanted to use this chip in this way. We wanted its platform to exist. It didn't, and so we designed this being engineers that needed it. And so we keep that in mind as we move closer and closer, or as we are guided by our North Star. Open source firmware. So like I said, this is embedded systems, so you can hook this with other microcontrollers or let it run completely alone. Here's an example of running over a microcontroller. This was on an ESP32, but we've had folks use STM32, MSP430. You could use like an ATtiny8. Folks have used this in micro-ROS as well. Open source software. We have ROS and ROS1 and ROS2 continually getting better. A programmer in our community wrote a Unity plugin, and there's a whole slew of fun reference pipelines, some of which you see here. And a lot of these are open sourced, written by the community, so you can just download them and run them. And one of the coolest things is this has been used for all sorts of other health and safety and just things we couldn't think of. Visual assistance. So that was just one guy. And he ended up with 100 articles written about his solution. So it was a visual assistance. It was like a chest mount that would tell a visually impaired person where they are physically, like on a sidewalk, approaching a stop sign, approaching a crosswalk. If a vehicle is on their trajectory, those sorts of things. Overhead trees, for example, that a cane would not detect. You can just use algorithmic depth, for example, for that. And then for various classes, you can run image classes or image classifiers, object detectors, and so forth. So there's all sorts of things that we couldn't think of that this was used for. One of which was on e-scooters and micromobility. So it's kind of like the inverse of keeping people who ride bikes safe, which is how do you keep pedestrians who are in the presence of these pretty high-speed e-scooters safe from the people who are riding the e-scooters. And with this kind of technology, you can just embed intelligence into, say, a fleet e-scooter that just does not allow them to go very quickly past a person or around a blind corner or in specific areas, say some semantic segment, and know that you're on a sidewalk and to not allow it to go fast. There's, sprayers that know, where they should spray, autonomous forklifts. This is a spatial dash cam, and then below is a prototype of the Commute Guardian. Actually, here's the AI in a backpack to help the visually impaired. Again, just one person, one very talented person, one person, and this is what we're so excited to enable. So where are we now on following our North Star? So it's broken down into 3 things. There's phase 1, mostly done. Phase 2, half done probably, and then the Commute Guardian implementation, which is not started. It's its own development effort, and we'll open source that as well. But phase 1 is absolutely necessary to really en vrai do Commute Guardian. Phase 2 are things that will help a lot. But once phase 1 is complete, a talented engineer would be able to build the Commute Guardian just on their own. Once phase 2 is complete, someone who knows how to make an enclosure will be able to build Commute Guardian on their own. So here's phase 1, so 129 things done, 8 in progress, very close to being done, and 2 left on the roadmap. So pretty close. So Commute Guardian efforts will be starting soon, above just concept, which I'll share later. Phase 2, so we show 97 done, 36 on the roadmap. If you look at those 36, those will explode into more, probably close to 100. As you dig into them and realize they're mini subtasks per task, probably multiplied by pi is probably a good rule of thumb. So we're about 50% complete. So what is required? What is guiding DepthAI's North Star? So there are all sorts of applications, like I summarized before, that only need some subset of these to solve them because of the industry. Interestingly enough, being on a bicycle trying to solve this sort of problem, at least from what we've seen, is the hardest problem you can solve with the platform. So it's kind of ideal in terms of guiding the feature set. we think it is solvable with the platform, but it's the hardest. There are other problems that are just not solvable with the platform. So this pushes all the way to the edge without going over. So here's the list of all the things. It's quite a lot. Most of them are done. Here's an example of lossless zoom plus encoding. This is useful when maybe you want to record 720p video to save space so you can record for a long time, but off of a 12 megapixel sensor, you can literally just record only where a vehicle is. So you get a great view of that vehicle, even though you're recording 1/12 the amount of information. In total, you're still recording the information that you want, which is the view of the vehicle that was going by, for example. So this is an example. Green is, oh, hey, the videos are playing now for some reason. Green is, we're just detecting a person. Yellow is a cropped area. This is actually a 12 megapixel source off of OAK-D, DepthAI OAK-D. And then yellow is the area where it's cropping. So this is cropping from 12 megapixel, actually I think to 4 megapixel, but you could go from 12 to 1 megapixel to go to 720p video. So it's a 12x reduction. And then this is that cropped area, like the 4K, which is 8 megapixel out of the 12 megapixel. And this is literally just taking the object detector and feeding that in. So there's, encoding. Encoding is a very important one. This is one of the ones that we just recently finished, which is edge filtering, which can be really useful in a lot of cases. So this is, if you want to buy a DepthAI just for this, I would recommend it. It's super fun to play with, and it's real time. So there's one, I should have put the video on here, where I happen to have a shirt that's like this artistic shirt with a road on it. And it even has like a perfectly segmented road. Like, even though it's an artistic shirt, you see the lines down the middle and the sides. Like you could have a little robot drive down my shirt guided by that. So edge filtering has a whole bunch of uses: improving depth, associating depth with semantic segmentation to a vehicle to get very accurate edges of the vehicle for predicting impact and so forth. None of which we've done. We just have an edge filter, but that's where it comes to the actual Commute Guardian thing. And then this is a whole bunch of functions in one. Harris Harris or she Tomasi filter. I have no idea if I said those names right. Feature tracking, optical flow. So that's feature extraction is the first one. Optical flow to tie those together so you can know one feature to the next. Motion estimation is used in this as well, and then it's integrated with IMU to aid movement. And so all of these then can be tied together for visual inertial orientation and trajectory prediction, which you need to do to estimate where is the bicycle, what is just oscillation from pedaling, and what is the trajectory of the bicycle, actual trajectory once you remove the oscillation, and where is the trajectory of the vehicle to quantize risk. So where does Commute Guardian stand? This was maybe 3 months ago or something. Sean from Nordling reached out. This one is apparently refusing to play. So he took 2 weeks. So he's from Nordling. They do a secure, privacy first data platform. They took OAK-D, threw it on a bicycle. This is what OAK-D sees. So that's the colorized depth view. That's it initializing why you see that kind of cool effect. There's a vehicle going by in depth. And then on the upper left there, it's showing the distance or the 3D location relative to the biker. Our bird's eye view is actually plotted wrong. We plotted X, Y, and Z wrong, so kind of ignore that. But actually the results were right. We just plotted it wrong and then produced the video with it wrong. So you can see X, Y, and Z. So there's left and right global shutter, which is what makes the depth. And then there's a color center, 12 megapixel. This is all on DepthAI. This was plugged into a Pi for data logging, but we actually have one of our system on modules now has eMMC and micro SD. We haven't put one of those on a bike yet, but you'd be able to do everything you see here literally with no other hardware, just with a battery. So this is where it stands now. What it's not doing, it's not doing visual inertial orientation. It's not doing platform motion estimation, but it knows where everything is. And here's OAK-D. It plugged into a Pi and a battery bank front and back of the bicycle. So that's where it is now, just kind of another proof of concept now that we've built this. And that's it. That's our North Star. That's what we're building towards. And with that, I'd love to open it up to questions. In one unsolicited piece of advice, especially since there's a lot of folks in the audience that are in school. how can you just generally help in the world? Double down on what you're passionate about. That's what I found. I love this stuff. I think it's super cool to be able to have an impact if that's what I'm doing, but find what you're passionate about, double down on it. If that happens to align with what we're doing, please reach out. My email's here, brandon@luxonis.com. We have our Discord. You can join anonymously, which is kind of great for Discord. But don't be surprised if I happen to know you in person here on Discord. I have no idea who you are. Our discussion forum, our docs are there, and you can check out our open source components. Thanks, everyone.
I think we are on online session now. So
okay.
Very thank you for your presentation, and very thank you you're willing to come this Q&A session. I think it's very interesting presentation. Now we have gathered some questions, so I think we can directly move on to a Q&A session. And in the same time, if audience want to ask any question, please feel free to put it in the chat. We will gather that also. So the first question is, the work you are doing is impressive. What have you on purpose decided to not implement for OD that you think would work and be useful?
Yeah, what have we chosen to not do intentionally? So that's a really good question. We're not doing anything that has to do with security cameras. So my thought behind that is it's just like consumer electronics. I've known a lot of folks in my circle or not in my circle that are like, oh, consumer electronics, I'm gonna do that. Like I know about my home in this thing that's annoying to me in my home. So does you know that, and so does everyone else, right? And so to me, security cameras and AI, it's kind of just like the first thing that everyone's like, oh man, like AI would be useful for security cameras. It's like, yep, you and every other smart person has thought of that. And so there's this huge oversupply of intelligence and time being thrown at making security cameras, which just means if you throw your life into doing that or your effort into doing it, you're just likely not going to get many fruits from your labor. If everyone's all doing the exact same thing all the time, unless you need a bajillion of them, which security cameras you kind of do, it just means to be hyper competitive and really difficult, and you're just not adding value. And so we got a lot of initial pull in like, well, you should make security cameras. And so that was probably like, if you were to rank the things of like the thing that we were asked for the most and then didn't do, it's that, right? There are some other things like, multi-camera, like real-time stitching that actually our platform would be good for. And I think, could be a great feature, but it's a really high ask, and it has kind of like a limited audience. We'll probably do it later. But the thing that we're really avoiding that gets asked for a lot is building a security camera out of this.
Yes, thank you.
Mm-hmm.
The other question is, for the hard synchronization, what is the limitation speed it can catch?
Yeah, so we actually have data on that on the hard sync. I'll see if I can pull it up so I can just tell you actual numbers. So it's sub millisecond for sure. And then let me see. Request. It's probably already. So the yeah. So the worst case is with like RGB cameras synced to grayscale that actually don't have hard sync, and so we do a firmware equivalent of hard sync in there. And so this is the worst case offset, but this shows the left right as well. So I'll actually just share this. So we just updated this. We had our Gen 1 API, and then we're bringing an improved version from our Gen 1 API for the hard sync. So it's tricky because these differences are in milliseconds. So this is 0.7 milliseconds, so 785 microseconds. And this is when the thing first boots up. So it hasn't had time to really start the synchronization. So you can see that, kind of oscillates around a little bit after 12 frames or 16 frames, maybe you're under 100 microseconds. And after that, looks like the worst case is maybe 70 microseconds between RGB to grayscale. And then right to left is what has the hardware synchronization. And so this comes down to measurement error as well. They actually might be better synced than this, but you're looking at 11, 10, 9, 12 microseconds. But that comes down to our capability to measure how offset they are. And then this is a view of the sync, so left and right, and then grayscale of literally just pointing at a device or at a timer.
Yes, thank you for your detailed explanation. The next question will be, you have selected a very challenging North Star and you are well on the way. Could you provide your best estimate of the final size and battery life of the Commute Guardian for bikers?
Yeah, that's a great question. So, this gives an idea of just kind of like the electronics. This heatsink, you could just build into an enclosure, but to just give an idea, when you put it on a bike, this isn't really like the form factor you'd want. It'd probably be, because generally on a bike, you just want it to like adhere to the seat post. So this is about as wide as a seat post. This is closer to the form factor. And this has everything that you'd need. When you build it into an actual like Commute Guardian, you just make the Commute Guardian out of aluminum, similar to like an OAK one is completely aluminum. So to give you the size, so imagine this, but a little bit taller. And what we're thinking is without any optimization, so you're just running the thing full out all the time. So you're doing all these features all the time when you don't need to. You're looking at probably 10 hours of battery life out of a worst case out of like a 10 amp hour battery. And you're probably looking at higher than that, maybe like 15, 10 hours maybe is probably a good estimate. But the thing that we want to add as well, which is coming like Q4 of this year to the API, is some more intelligent like power thresholding modes. Like for example, in the Commute Guardian, you could do an image classifier to start that's running, that takes way less power. You're not calculating 3D trajectory or platform motion or anything. You're just doing an image classifier at some frame rate, maybe 5 frames a second, which just detects if there's a car behind you. And when you do something like that, instead, you could very reasonably extend the battery life to maybe 20 hours because it's just sipping power, telling, is there just a car in the scene? And when there isn't, then it's obviously doing a lot less. It's just effectively being a bike light this with a low rate image sensor. And then once there's a car in the scene, then it can kick into like overdrive of doing spatial sensing, platform motion estimation, trajectory estimation of the vehicles, H265 encoding, all those things that can push this more up to 1 amp pulling off the battery. But when you're not doing those, maybe you're taking like 50 milliamps or 100 milliamps or something like that. So I think an initial version would last maybe 10 hours. We think probably early next year, I think it'll be reasonable to have like production like prototypes of the actual Commute Guardian. Maybe earlier if the chip shortage isn't super painful. And our model is, we would not be building that directly, but we'd be working with a company enabling them to build it. Anything we build directly, though, we will just open source to make it easier for any company that's building that sort of thing.
Thank you. Next question is, could you tell us a little about the data pipeline architecture that you are using for the common guide? How many algorithms do you vision will be running in parallel, and what estimate do they provide?
So the pipeline that would exist in the Commute Guardian, is that the question? Like all the CV functions that exist? I'm not sure if I understand it right away.
Okay, I think I will go to another question. Which algorithm that you have implemented brings the OAK to the edge of its capacity?
Oh yeah, what really pushes it to the limits? So it's a great question because there's a lot of neural models that can actually be optimized to then allow you to go further. But in terms of like maximum limits, there's a lot of different ways to push it to the edge. But what it really comes down to is when you run out of DDR bandwidth on the chip, which is pretty fast. But one example is the encoder. The maximum encoding is 8 megapixel at 30 frames a second. So you can do 4K video and dual 1 megapixel video. So it's 8 megapixel plus dual 1 megapixel at 25 frames a second. And then that starts to saturate the DDR bandwidth. And so then an object detector would run maybe at 20 frames a second or something like that. That's one of the ways to maximize, to push the chip in terms of power and utilization. I think you can run depth at that speed as well. Another is just straight up neural networks. So running some of these more complicated pipelines, say, a good example is we have this machine safety where it's tracking where your hands are in physical space and then tracking some other object that's dangerous. And we're doing depth realignment as an example on that, where it's running it on the RGB and realigning the depth, the grayscale depth to be centered on the RGB. So you kind of get the best of both worlds. That and doing multi-stage, multi-model starts to push the system where maybe you're a tad under 30 frames per second. But the interesting thing on a lot of these is that's kind of like the naive way to use our pipeline, and we're using it intentionally in that way to push it, and it's simpler as an example. But you can do things like lowering sensor resolutions and focusing on regions of interest and stuff like that then would make that pipeline actually not push the system at all. And that's one of the things that we'll be implementing, like maybe like Q3 to Q4-ish, is allowing those like hardware reconfigured of image sensors for, say, if you're tracking a hand, the hand can only move so fast in the frame. And so if you do the region of interest, reconfigure the grayscale cameras for that region of interest, then they can actually run at much higher frame rate while taxing DDR and taxing the neural networks, everything a lot less. And so this pipeline, when it's naively created, maybe runs at 30 frames per second, and that's about all it can do. When you do those sorts of optimizations, then you can get 60 or 120 frames per second out of it, and actually have headroom for other things. So it's very multidimensional. The pipeline builder is one of the fundamental infinite sort of. So there's no rigid structure your pipeline has to be in. It's only limited by resources. So do you run out of DDR because of the size of the neural models? Usually that's not what you run out of, but in some cases, say if you have a very large set of models, that could be, usually you just start to run out of performance. And then it's a matter of like, okay, how do you optimize this by passing fewer pixels in or more intelligently cropping or reconfiguring the sensors? So it's a bit hard to answer, but hopefully those give various limits.
Thank you. Let me try to pick out some questions from YouTube chat. So the question is about data path. What current restriction does it have?
Okay, restrictions on data path. So the image manip node is how you convert between various formats, going between, say, a feature tracker node or neural inference node and so forth. And that's one of the things that's probably the most limiting right now, is it only supports specific image formats. And so we're planning on improving that soon here to support various NV12 operations, where a lot of it's RGB right now. It does support grayscale operations, but to be able to interchange between all these formats. So it is a network on chip architecture, and it has these specific CV manipulation capabilities. The image manipulation node is our way of having a performant node that does all these conversions for you, leveraging the hardware. And so the hardware does support these things that we don't yet support in the node, but there've been more critical kind of bugs and blockers that have been preventing that. And so for most customers, we've unblocked them via another route. But the image manip node, let's see, I probably have it up, is one of the last things on that, when I said about kind of the Gen 1 feature release, is it's this, I'll share my screen here, this extend image manip node. This is funny, your internet only stops working when you're doing a screen share. So NV12 to NV12, NV12 to RGB, RGB to NV12, RGB to gray. You can actually do that now, but it's not as well supported as we want in upscaling. So this is probably the most limiting thing in the data path right now. There are a slew of ways to work around it, but it's one of the highest priority things left from our phase one. Motion estimation's mostly done. It should probably be an in progress, and then extending image manip. So we'll probably start on that next week or the week after, and then it'll be mainlined within a month, I think.
So from the same person, the second question is, connecting two OAK for complete 360 spatial view. Is that possible? I assume it's the question.
Yeah. So we have the OAK-D, but then we also have the modular camera. So let me see. I'll bring up some photos here. So if you're wanting to do a full 360 degree capture, I would actually recommend these. I'm gonna really make use of screen share here. So we have this modular version, and then we're extremely happy with Arducam, UC-Tronics, and so they've made custom devices for our platform. So with M12, with autofocus M12, which is what you see on the bottom here, and then we also it's not as clean as we want it to be, but you can technically connect multiple RGB, so you could connect multiple 12 megapixel or multiple OV9782 or AR0234, which are 2.3 megapixel color global shutter. So if you're wanting to do a 360, I would actually recommend this board, and/or we actually have, this is our OAK FFC-3P, meaning for 3 ports, and then we have a 4-port version coming out, which we're actually ordering tomorrow. But you could use the 3-port for now, or multiple 3 ports. So the 4 ports largely the same thing that you just saw there. We moved the ports to the bottom so they're a little easier to connect, and since there are 4 of them. And so with this, you'd be able to hook 4 cameras. You can, with the Arducam modules, you could use a 180 degree M12 or maybe 120 degrees, so you have overlap between all of them to give 360 degree view. So that's what I would recommend. You could definitely use an OAK-D, but these are only like 70 something degree horizontal. And you can actually buy Arducam modules that, like, if you're like a hacky type of person, you could take this apart, take the front cover off, and put Arducam's 120 degree horizontal on OAK-D and use it and recalibrate it, because we support mesh calibration. But I would probably recommend just kind of building a rig with these modular versions. Project North Star, which is open source, has done that. For example, they use 3 cameras with very wide field of view.
Mm-hmm. And the next question for scooter, commute, guardian, more stable than a bike. And here in Taiwan, there's a lot. Any possibility for implementing?
Yeah, I would love to see this on, it's like Scooter Commute Guardian. I'd actually like cold reached out to, I don't know, like probably 10 different scooter companies, but they don't know me. And our platform wasn't nearly as far as it is now, with the idea of like, you could definitely build this in. It's more stable. That's a really good point. And I love Taiwan, by the way. I've been there multiple times, three times. Actually, I was there in January 2020. So the last time I could like really get out there. And so I'm familiar with the scooters, and I love scooter culture and everything. So yeah, I think mainly it's just getting connected with the company. So if you guys know a company that would be interested, I'd love to talk to them, integrate the technology. As I kind of mentioned in the presentation, a lot of the stuff is already there. You could, in this, particularly with scooters, since it's a more stable platform, you could get an early alert system, and at the very least, you could have a really useful kind of like incident logging system already, where it's like, this happened, and I already have a log of the license plate, 4K video of the incident, and those sorts of things.
Very interesting. In terms of energy or other restriction, what is needed to implement the OAK-D on a drone?
Yeah, that's a great question, actually. So the Myriad 2 was extensively used in DJI drones, which I think is a great use of the chip's capability, and the Myriad X as well, I think fits really well. So the power modes vary. Right now, our API is very basic in terms of power mode. The Myriad X is actually quite capable in terms of how much you can vary the power use, because it's this power island system. So you can literally turn off whole sections of the chip. I believe it's around 30 parts of the chip are programmatically controllable to be actually fully powered down. But right now we don't expose any of that. We plan to do that at the end of the year. So the only like power control right now is just how fast you're running cameras. And then that just kind of slows everything down. So you can get it to go as low as maybe 2.5 watts on an OAK-D, maybe 2 watts. I haven't played with it that much. And then the max is about 5 watts. once we have those power control settings, I think you'd be able to go as low, depending on the scenario, as low as maybe quarter watt or something like that, where you're just running, like, say, an image classifier or something like that, and then scale that all the way up to 5 watts, depending. But right now it's around 2.5 to 5 watts.
Thank you. Our session will end around 5 minutes, so I think this one will be the last question. Okay, so this one is, hi, we are a group of bachelor students planning to work on a real-time video surveillance anomaly detection system. What do you think about a possible implementation of this project using OAK?
Yeah, I mean, I think you could do anomaly stuff with us for surveillance. I would say there's probably other platforms that'll work better, kind of like I was saying earlier for surveillance. And I dug into like one aspect of it earlier when I talked about just the amount of people working in that area. And so there are good chips for it. The other aspect, which is a bit more technical in the Myriad X, is, right now the world is kind of given a specific capability, max capability for the die of producing chips. The Myriad X has taken a huge portion of that die and dedicated it to things that are only relevant if the platform is moving. So, a lot of those features, like the tight IMU integration with everything, are for a moving platform, and it's extremely useful. When you're doing surveillance, if it's fixed surveillance, all those become useless or mostly useless. So you look at this die and you're paying a certain amount of money for the whole thing, and then this whole subset of it is effectively useless to you. And so that makes for surveillance. There's a lot of other, say, umbrella chips or other platforms that don't have all those features that the Myriad X has, that aren't nearly as capable on moving platforms, and aren't intended for moving platforms, but are then specifically targeted and a lot more useful for fixed surveillance applications. So you could do it. We have a great API. maybe that's excuse enough to want to use our stuff over others, so we make things easy. But I don't want to say our thing's best at that. What I would say our thing is best at is if you want to integrate it into some tiny thing that moves. If that makes sense.
Yeah, thank you very much. I think we still have some question. Would you mind, after this Q&A session, we send you the mail and we
Sure.
give you the questions? Yeah, that would be fantastic.
Yeah, absolutely. Yeah.
Yeah, thank you very much. This is the end of the Q&A session. Thank you very much for joining us.
Yeah, thank you for letting me talk. Thanks, everyone. Yeah. Thanks, everyone, for watching.
Thank you. See you. Bye.
Bye.